Okay, welcome everybody. Good evening. It's my pleasure to welcome everyone to the annual Emilio Segrè Lecture. Since 1987, by the way, my name is Steve Boggs. I'm the chair of the physics department here at Berkeley. Since 1987, Berkeley Physics has had the opportunity to bring world-renowned scientists to our campus to speak in honor of one of the greatest experimentalists of the last century, Emilio Segrè. The lecture series, which occurs each fall, highlights trends, discoveries, groundbreaking research, and is made possible through the generosity of the Raymond and Beverly Sackler Foundation. Emilio Segrè was one of the 20th century's most distinguished physicists and was one of our esteemed faculty members for more than 5 decades. Together with Owen Chamberlain, he won the Nobel Prize in 1959 for the discovery of the antiproton. He had been a student of Enrico Fermi's in the late 20s and later a professor in Palermo. But while on a visit to California, Mussolini passed a law barring Jews from obtaining university positions, and Italy's tragic loss was America's gain as he was unable to return to his home country. He became a group leader for the Manhattan Project at Los Alamos National Laboratory, and eventually a professor here at UC Berkeley in 1946. Today, we're fortunate to have his grandson, Gino Segrè, and his wife, Kate Gordon, with us to also honor his legacy. So Gino and Kate, we just want to thank you guys for joining us. Surprise! Past Segrè lectures have included former Chancellor Robert Birgeneau, Hans Bethe, Herb York, Masatoshi Koshiba, Burt Ricker, Mildred Dresselhaus, Andrew Lang, and this year's Nobel Prize winner in physics, co-winner Art McDonald. This year we're pleased to add to that list Stephen Chu, Berkeley alum, Nobel Laureate, former director of the Lawrence Berkeley Laboratory, and former Department of Energy Secretary. His lecture entitled A Random Walk in Science takes us on a journey of remarkable career, one that started here at Berkeley with his mentor, the late Professor Emeritus Eugene Commins. Professor Commins passed away last month. It was a very sad event in our department and on campus. He left his mark on the campus and with his students as a scholar, extraordinary educator, and esteemed colleague, and he will be deeply missed. Today, his wife, Iris, and his son, David, are with us, and I want to just thank them for joining us. Iris and David, could you please stand up for a second? Thank you both very much for joining us tonight. And now, let me actually introduce our speaker, Stephen Chu, who's joined by his wife and our good friend Jean Chu tonight. Stephen Chu is the William R. Keenan Jr. Professor of Physics and Molecular and Cell Physiology in the Medical School at Stanford University. His research spans atomic physics, polymer physics, biophysics, biology, biomedicine, and batteries. You're making us all look really bad, Steve. He shared the 1997 Nobel Prize in Physics for laser cooling and atom trapping with Claude Cohen-Tanuji and William Phillips. He received degrees in mathematics and physics from the University of Rochester in 1970 and a PhD from UC Berkeley in 1976. Following 2 years as a postdoctoral fellow at Berkeley, he joined the AT&T Bell Laboratories in 1978 and in 1983 became head of the Quantum Electronics Research Department. While at Bell Labs, Chu first demonstrated optical molasses laser cooling, optical tweezers, and the magneto-optic trap, the 3 most widely used methods in laser cooling and trapping. In 1987, he joined Stanford University. He served as the Theodore and Francisca Ball Professor of Physics and Applied Physics, twice Chair of Physics, I feel your pain, Steve, and helped launch BioX at Stanford University, a multidisciplinary institute combining the physical and biological sciences with medicine and engineering, and the Kudley Institute for Particle Astrophysics and Cosmology. In 2004, he became the director of the Lawrence Berkeley National Laboratory, rejoining us here in Berkeley. And then in 2009, he stepped down to become the 12th U.S. Secretary of Energy, a position he held until the end of April 2013. He is the first scientist to hold a cabinet-level position and was the longest-serving energy secretary, recruiting numerous outstanding scientists and engineers into the Department of Energy. After completing his government service, he returned to Stanford and is currently doing research developing new nanoparticle probes for optical imaging and their application to studies of live organism imaging in neurobiology, cancer signaling, and biofilms. He is developing next-generation batteries and other applications of nanotechnology. Holder of 10 patents, Dr. Chu has published over 260 scientific and technical papers. In addition to the Nobel Prize and numerous other honors, he has been awarded 25 honorary degrees. He is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, National Academy of Inventors, the Academia Sinica, and a foreign member of the Royal Academy, the Royal Academy of Engineering, the Chinese Academy of Sciences, the Korean Academy of Sciences and Technology, honorary fellow of the Institute of Physics, and of the Optical Society of America. We are thrilled to now add Segrè Lecture to that list. Please join me in welcoming Dr. Stephen Chu and thanking him and his wife for joining us tonight.
It is truly a pleasure to be here and give this Segrè Lecture in honor of Emilio Segrè, to visit back at Berkeley, and I've spent many, many happy moments here at Berkeley. I also want to mention my advisor, Eugene Commins, who, can't really say much, I was going to get all goofy, so anyway, so I'll just move on. All right, so let me plot out. This is a kind of a confession of a career, a very checkered career, and to the younger people here, you know, there are milestones in a person's scientific career. You have the first contributed paper. You give your first invited talk. You're going up in scientific standing. Then you're asked to give a first plenary talk. And then, because of rate inflation, they have something higher than that, and it's called a keynote. And then afterwards, something begins to happen. You start to get after dinner talks. Okay. And then you maybe could talk about other people's work after dinner talks, going further downhill. Begin to mess them up, giving after dinner talks, and then you become a bureaucrat and speak on certain occasions. Right. Now, I want you to notice something. There's an axis to this, and that's 0. And you can go negative. And you begin to reminisce about the good old days, but you butcher the history. So this is a butchering of some history. All right. So let me talk about random walks. You know, life is a series of random events, many random events. You don't really able to choose your parents with any authority. And let me give you an example. This is a picture of my mother and father on their wedding day. It's 1946, and you look very, very handsome couple. And talk about a random event. How could you ever imagine they could have a baby like this? So, and it's just not a bad hair day. It goes like that. Okay, so I'm going to fast forward and talk about my time at Berkeley and in the Eugene Commins group. University of California, Berkeley, when I came in 1970, was spectacular. There were 9 active Nobel laureates in physics and chemistry. There, if you count Macmillan as in physics, and you know there were 6 in physics. And I love this picture because you can actually see LeConte Hall. And so that was also spectacular. What I didn't realize while I was there in the 70s that Berkeley had some graduate students who went on later, and these are the times of their PhDs in chemistry, MCB, and physics to get Nobel Prizes. It was an amazing place. So I joined Gene's group. Gene had some spectacular experiments in time reversal invariance, but he always had a very small group, and those people were leaving. And I overlapped with a couple of people. One was Stuart Freeman, who was a faculty member here, for a very distinguished faculty member. And that's Stuart on the left, and Mel Simmons on the right with the t-shirt acting deputy head. And they were kind of like the Bobson twins, they were inseparable. And the three of us shared an office together. And I was this young kid and they were, leaving, and I would always have a messy desk, and it would just sort of spread out onto the communal table. And it got so bad that Stuart laid down a piece of black tape on the floor and on the desk and said, "Your space, don't go any further than this." And so that's what happens with senior graduate students and junior graduate students. So let me tell you, so I began to work with Gene. First quarter I took a class from him, and it was an inspired lecture. And since that first quarter of that first class, every class he taught, I would make sure I would take it. But I started out, and he actually assigned me a theoretical problem of protostar formation, not what he was doing, but what he wanted to move into astrophysics. And I worked on that for 3 months, and I got it incomplete. After a few months, I would sneak into the laboratory and do play experiments. And finally, I told him, "Gene, I think I want to be an experimentalist." So he kind of looked at me and said, "Oh, okay." And so he said, "Well, there's this beta decay experiment, and maybe we can do something there." I worked on it for a year with him. By then, he became chair of the department, and this was at the 88 cyclotron, and it went nowhere also. So I got another incomplete. Then, he said, "Well, you deserve something better than this experiment, so we'll go looking around." And at that time, I said, "I really like lasers, dye lasers." This is in the early 1970s, 72, and I was talking with some Ron Shen students, and I said, let's do an experiment with lasers. And I don't know anything about lasers. Don't worry about it. We'll just do an experiment with lasers. So he found one with Richard Maris, the lamb shift of Pi Z, and so we're working on it for about a year, and got another incomplete. All right, so what was happening? So what was happening in the late 60s and early 70s was something spectacular. There was a proposal of unifying the electromagnetic interactions with the weak interactions, which described radioactive decay. And Weinberg, Salam, and Glashow had proposed in the course of 67, 68, and a little earlier with Glashow's work, that it may be possible to make this a single unified theory. Gene was an expert on weak interactions, beta decay. He had written a textbook, and so I said, "Well, what about this?" And he said, "Nah, it's just a speculation." But what changed his mind was in 1972, other individuals, Tuft and Veltman, showed that some of the ills of the previous Fermi theory could be curable. And so he said, maybe there's something there. And then Marie-Anne Bouchiat, and her husband, Claude Bouchiat, published a paper in 1974 that suggested maybe you can see the effects of this new theory in atomic physics. And, okay, so I read the paper, Gene read the paper, and we decided we're going to stop what we're doing. Just stop completely and work on this. And so there I was, a graduate student, 3.5 years, started my 4th experiment, and it was, so I worked on this for 2 years. Then Ralph Conti joined a little bit later, and after 2 years, I went to Gene and I said, I've been a graduate student, I'm going on 6 years, I'll make you a deal. Give me a PhD, and I'll stay, and I'll finish the experiment. kind of looked at me and said, okay. I said, oh, I suffered enough. No. Anyway, and so it was actually good for him because I was an NSF fellow, but the last 2 years, they only give us 4 years. And as soon as I became a postdoc, I became an NSF postdoctoral fellow, so I became free again. So it was beneficial. All right, so during that time, I started building dilators. This is me before the face change. A lot more hair and look younger. And so, and in this picture, there's a picture of a gizmo thing, which was a dye laser that I had built up. And it worked very well, but that's okay. We needed a workhorse laser, you simply couldn't buy it. All right, so my PhD thesis was not parity non-conservation. We couldn't get there. So it was a measurement of the precursor, just the atomic transition. And so if I had to give myself a grade, it would be a C. And this is now finishing my 6th year as a graduate student, okay? And so we were all excited. We thought this was a great piece of work. We submitted to Phys-Rev letters. It was rejected and said, you're not measuring parity non-conservation, so we're not going to publish it. So, all right. Okay. So 1.5 years later, in the spring of 1978, Gene says, we'd like you to apply as assistant professor at Berkeley. So I said, oh, really? Published one paper. One side got published, okay. And I said, well, yeah. And so I had a job talk. It was in the physics department of Clothing. There were about 400, it was like 1 or 2 Lacan, I forget which one. There were 400 people. And I remember going before, there's another researcher named Mike Pryor who said, let me give you a warning. Well, I got 2 warnings, one from Gene, one from Mike Pryor. He said, Emilio Segrè will be in the audience. And so make sure you know what you're talking about. Because he might raise his hand and say, I remember Enrico and I were thinking about this long, long ago. So, okay. All right. And Gene Commins gave me, he says, I'm not going to tell you what to say or what you're going to talk about, but I give you one bit of advice. Whatever you do, don't give the lecture in tennis shorts. Because I would always walk around in tennis shorts. Okay, so they decided to offer me an assistant professorship. I took the job. They gave me $25,000. I spent it that early summer. To buy a dye laser system and a pulse ag laser system. Okay, so and then that fall we submitted another paper. I'm there down in the author list. This is now Ralph Conte, Phil Watsmow, me, Gene Commins, and Larry Hunter. And Gene was great. He said, now I know you really did a lot in this experiment, but you have a job, so I'm going to put you far down the author list. So I said, I don't care. And so he was looking out for the next person. That was very classic of Gene. And so that was fine. This is what I look like. This is with some Polaroid camera that Percy Trell, she was beginning graduate student at her first year, and I worked her for the first summer where she began research. Now I want to draw your attention, you probably can't see this, but in the background, there's a crop picture of someone, it looks like a little baby with a noose around the neck being hung. And it's W.C. Fields. And so this is Gene's type of humor. So he would put up artwork, strange art like this. And he loved W.C. Fields. This is the laser person I built. So we spent the summer machining these parts and building it up. But I want you also to notice something. I'm going to now change the contrast of this thing. By the time I was supposedly entering an assistant professor job, I didn't really know much physics, but I knew how to build lasers and I knew how to scrounge stuff because we were told to buy a lot of the stuff until my start money. But there's another thing that Gene added. We build the laser, we punch the hole through the wall, the laser light goes to the next room where the experiment was, and so Gene decided to decorate the hole. And so he actually put up this clown's face. That's all Gene. Anyway, so that's one of his terms. So in my 8 years, I learned a couple of things. I learned that it's really important to work only on fundamental questions, that it's okay to change course and abandon what you're doing before completing it, and it's also okay to stick with it for a long, long time. So I was the first student, and then Ralph, and then Phil Buxbaum, and then Larry Hunter, then Persis Drell, all working on the same experiment in various generations. The first one was really lousy. I can tell you our result was really stinko, my result, or the first generation, and it got successively better. Also, the importance of writing clearly. Those of you who don't know, Gene's father was an editor. His name is Sax Cummins, and he was an editor of Mr. Random House. And Gene Commins was Eugene Commins because his godfather was Eugene O'Neill. And he was an editor for Eugene O'Neill, but he didn't talk much about Eugene O'Neill. Gene did talk about William Faulkner a lot, who was another person that they had a house in Gene's family in Princeton, and he said that Faulkner would spend weeks at a time writing upstairs in the little loft. He would come down and he'd give on the kitchen table 3 pages of manuscript, and I said, "And what do you tell Faulkner how to write about it?" And he said, "Well, you know, character development, this inconsistency." And so Sax Cummins would make corrections and leave them on the kitchen table because Faulkner was sleeping during the day and writing at night. And to make sure the breeze didn't blow away the piece of paper, there was a bottle of bourbon on top of it, a new bottle, and every morning there was an empty bottle. And some more pages. But Gene's writing style was very spare. It's more Hemingway's. But he really appreciated good writing. I wrote a thesis. I wanted to get it done really quickly, so I wrote the first draft in 2 weeks. I gave it to him, and he said, "Well, let me go back into the lab." And he kind of looked at it. Instead of just crawling with red marks, he just gave it back and said, "You can do much better." And just gave it back and said, "Be more precise. Let the reader know exactly what are the ideas and what was done." And just hand it back. And so 2 weeks later, I gave him another draft, and he said, "That's okay." And then he let me back in the lab. Now, Gene was a master at taking a known technology, atomic beams, and improving upon it and driving it to where you wouldn't believe it, and with exacting rigor and systematic effects. He was so good at that stuff. And I couldn't really figure out, is this my strength? And what I learned from other professors at Berkeley at the time was that if you're going to do something and you're not as smart as Gene, a lot of professors were very, very smart. Charlie Towns would invent a new technology and apply it to a new field, astronomy. Ron Chen, nonlinear optics. John Clark, interference and squids. And all it, so from these others, I began to realize that there's another way of doing science, and to maximize your ability to make new discoveries if you're not that smart, invent and develop a new technology and to be the first to apply it. And otherwise said, if you're the 100th person to look at the same problem with the same tools, you'll probably not find anything new. So I learned that from the other great scientists at Berkeley, because actually I was not like Gene in that respect. I was kind of goofy. Okay, so I then I went to Bell Labs as a leave of absence. It was amazing because when they gave me the appointment, they said there was a lot of discussion. You spent your whole time here working on one experiment, and we want you to be a faculty member here. You're welcome to start your own group and do whichever you want, but you're also, you can take a leave of absence for 2 years, go anywhere you want, but you're a faculty member, and I said, great. So I decided to go to Bell Laboratories for 2 years. And so at Bell Labs, another very checkered past, I worked with 2 former Berkeley students, Hyatt Gibbs, who was a student at LBNL and a postdoc with Gene, and Sam McCall, who was the student of Erwin Hahn. And we worked on some problems. Phil Anderson at Bell Labs had just gotten a Nobel Prize for what was called Anderson localization. And he said the only real proof of this was this one experiment done in optics. And Hyatt said to me, you know, I know you want to do other things, but why don't you join us and figure out, you know, you can strengthen the claim. And so we worked on this energy transfer, and after a couple of years we found that the system didn't even apply to Anderson localization. And it was not a null result, it was a result that said the first set of experiments were incorrect. So, all right. Then I worked on laser spectroscopy of positrons and electron and antiparticle, something really in the commercial interest of AT&T telephone company, with a fellow by the name of Alan Mills, and later Jan Hall joined us. It was a good experiment, and ultimately we were able to make a precision measurement of a few parts in a billion, but it went nowhere. Well, you know, it got some notoriety, but in terms of science, it went nowhere. This is what I looked like at that time. Laser cooling and trapping of atoms, I started work on, and that actually worked better than expected. So I'll spend a little time on this. So here's the idea. Suppose you have an atom that's going in a certain direction, like to the right. And if you know it's going to the right, you can take a laser, scatter photons, particles of light on it, and you can slow it up. But what if the atom is going to the left? This will not slow it up, it will accelerate it. And so this is a problem. So if you know which way it's going, you can slow it up, but to cool something, you're taking out the random temperature. And so the idea was that you put another beam on the opposite side and use what's called the Doppler effect. And so the Doppler effect is fine. If you're an atom and you're moving towards the laser beam on the right, I'm going to move towards you. And as I move towards you, my voice goes up, and I move away from you, my voice goes down. So if you tune the laser so that if the atom's moving towards the beam on the right, it goes more in resonance, more likely to scatter. Running away from the other beam, less likely to scatter. So that was the idea. The atom goes in this direction. You can use 2 or more laser beams. And this was a wonderful idea. It was too good to be true. I said, I couldn't believe this. This is amazing. So I told I was then a department head at Bell Labs, and I went to my boss and I said, this is going to be amazing. And he kind of looked at me and said, because you can maybe trap atoms once you get them cold. And my boss was Chuck Shank, who was LBNL director for 15 years after he was at Bell Laboratories. And he had shut down the program 4 years ago. So he said, okay, you're allowed to do this. Don't try to talk anyone else into doing it. Okay, so I said, fine. And then at the very end of the last couple of months, I said, hey, this is going to work. So don't bother. We don't have to ask permission. So it was going to work. And so from the time this quote rediscovered the idea, the time I sat down to write the first draft, it took 10 months, and I didn't have a vacuum chamber. The whole experiment was 10 months. So I did, and then Ari Ashton says, you should read this paper because it has something with what you just did. I read it, it was the Shallow-Hench paper, and I said, oh my God, it's everything I did, so it was reference 1. So it worked very well. We got atoms very cold, but I messed up here too. Because there were early signs that they might have been colder than theoretically expected. I kind of ignored them, I put in big error bars. And then Bill Phillips and his colleagues remeasured it because there are nagging signs, and they said, holy smokes, the minimum temperature, expected temperature was 240, Oh, that's not Kelvin, it's micro Kelvin. Apple to PC Apple. So it's millionths of a degree above absolute zero, and so it worked much better than theory led us to believe, and so you call this a strong violation of Murphy's law. Right? You know, why is it working so well? And then it was clear that the theory was just a ground state excited state of an atom, so there must have been something in there because it was a complete QED theory. And so there was a little bit of scrambling, and within 6 months, Jean Dalibard and Claude Cohn-Bernouillet and I independently figured out the quantum mechanics of this. And so, and that was done in '88. All right. So a lot of things happened at Bell Laboratories, trapping of atoms, the magneto-optic trap, all those good things. But then I decided perhaps I should go back to academia, and so I had to decide between Stanford, Berkeley, and Harvard. And Gene, again, said his recruiting style was subdued. And he said, why are you even considering Stanford? Because instead of being a big fish in a small pond, you can come to Berkeley. And he was right. At the time, Berkeley was heads and shoulders above Stanford. Stanford was a very small 22-person, 21-person department. They had some really good people that they were either dying, retired, or about to retire. And so in the next 10 years, 40% of the faculty would turn over. And so, and I said, you know, so I rooted for the underdog and decided to go to Stanford. Now, you might be asking yourself, why would you be interested in cooling atoms to these ridiculously low temperatures and holding on to them? And I have to confess, when we first were able to cool and trap atoms, I went up to a former director, my former boss, Bill Brinkman, and I saw him in a meeting. He said, Bill, guess what? We cooled and trapped atoms. And he knew I was very excited. And he said, Steve, that's great. As a good manager, you never want to, you know, dampen someone's enthusiasm. And he said, and what are you going to do with it? And I said, Bill, I am the foggiest idea. It's really neat. So this is a big departure from Gene's training. You know, it was not a fundamental question, a deep thing. But nevertheless, let me tell you one application I knew about when I was at Bell Laboratories. You can make a better clock. Oh, what does that have to do with anything? So, and so when I got to Stanford, we did the following. We took this ability to trap atoms, we get them really cold, and you can toss them up, and they can turn around due to gravity. And in the time they're in free flight, turning around due to gravity, you have a long time to make a measurement. And so with that, you say, okay, this so-called atomic fountain will make a better clock. The NIST people, the French group got into this. Very soon we did a second experiment in the cesium, and we exceeded the short-term stability of the clocks. Within 7 years of contributions all around the world, the atomic fountain became the time standard. And so a very, very short time from the time you first do a demonstration experiment to it's the method. Now, a lot of water has passed on the bridge since this time, 1989. There are now optical clocks using cold atom technology that are really going to surpass anything you could dream about in the microwaves. And I'm pretty confident they're going to achieve an absolute accuracy of 18 decimal places. What does 18 decimal places mean? If you had a clock when the universe was born, and you asked today, 13.8 billion years later, what time is it? You would know within a fraction of a second how much time has been spent. Now you're asking yourself, you don't need that accuracy. Aren't you just showing off? The answer is, of course we're showing off, but not really. The most precise measurements in all of science are frequency or frequency shift or so-called phase shift measurements, which is the best way of measuring frequencies. And for that reason, the length is defined in terms of time. How far does light go in a certain number of oscillations of a cesium atom? The volt, the ohm, because of wonderful quantum mechanics, also can be defined in terms of frequencies. And the most accurately known physical constants, for example, Planck's constant by the mass of the atom, which will lead one to the Fine-Schuster constant, can also be measured this way. And the most sensitive tests of fundamental symmetries, like time reversal invariance, or looking for an electron dipole moment, are actually phase shift or time, frequency phase shift measurements. And in fact, Eugene Commins spent his second time after the parity stuff, and he went back to time reversal, and he pushed that technology even further. And so, Gene and his group held the record for the best measurement of whether an electron has some structure. It's just not a point particle. Succeeded only recently by a former student of Gene's, Dave DeMille, and John Doyle at Harvard. And this measurement is so exquisitely precise that it's setting very stringent limits on whether there could be supersymmetric particles that may or may not be discovered at the Large Hadron Collider in CERN. So it's one of those, another amazing things, of very, very fundamental science that can be done in a laboratory. But let's go back to the goofy stuff. So when I was at Bell Labs, Art Ashton used this focused dipole trap to trap bacteria, and he was going great guns, and he could move them around, he could do all sorts of things and torture them. And when I got to Stanford, I said, is it possible, well, we can trap atoms, we can trap bacteria and stuff within protozoas. So is it possible to hold on to a single molecule by gluing a little sphere? The handle was that little sphere and in a focus beam. And so you're going to see a movie of that bright sphere is a little polystyrene sphere held with an optical tweezer, focused by the optical microscope, and where the laser is focused, it can be moved around with a joystick. And this is what you can do. So that line of light is a single molecule of DNA. And to my graduate students, it was like playing computer games. And this is what they did for hours and for days. And they were thrilled by it. And I finally said, okay, guys, I know you're having fun, but we should do some experiments. All right. So I should also say that as I was going into biology, a high-energy theorist came to me and said, you shouldn't do this. I said, well, why not? I said, because the laser cooling and trapping of atoms is gaining real momentum, and if you go into biology, you might be written out of the history, so you should stay in physics so they remember your scent. He actually said it that way. And I said, nah, I don't think so. So I was doing physics to be sure, but I was going to biology. Now, luckily for me, so this was all done starting in 1990, 91, 92. Fortunately for me, they did remember my scent. This is Eugene Commins with my mother. You're looking, Eugene is kind of listening to her. My mother's a very talkative person. And my mother was saying, you know, he never listened to me. How did you get him to listen to you? But Gene is very quiet and diplomatic, didn't say anything, but this is probably what he was thinking. What makes you think he listened to me? Okay, so this is December 1997, Nobel Prize ceremony. This is a co-winner, Bill Phillips. Physicists are, you know, it goes physics, chemistry, medicine or physiology, literature, pieces given in Norway, and the physicists are always, since it was mentioned first, they're held in the highest regard formally in the ceremony. And the physicists get to sit next to the king and queen, so this is Bill Phillips with the queen. And so, did I feel bad about that? Not really. I get to sit the crown princess. Anyway. So I'm going along, we're doing lots of things in physics and biology and atomic spectrometry. Things are going well. And then Burt Ricker says, you know, LBNL's looking for a new director. I think you'd be great for the job. I said, no, I don't want a job. I don't want to be a big... Believe it or not, I didn't really want to be a chair of the department either. But it was a deal that I made in 1993. There were three of us who said, well, there has to be a new generation, and we wanted people to serve the department and not their subfield or themselves. And so I, Doug Arsham, and Boss Frere agreed that we would help each other and we would do it successfully. And then it went, and so then that's what happened. And then the next time around, no one, so I said, okay, I'll do it again. And then Doug did it again. Boss said, I'm not going to do it again. But that's why it happened. I didn't really want to do this. Chuck Shank calls me and says, you know, we'd like you to throw your hand in the ring. I said, I don't really want to do this. I love what I'm doing in the lab. So he says, look, if there's a 5% chance you might consider it, come and look around and go for an interview. If it's less than 5%, forget it. So I thought, by this time, this is 2004, I thought, I really was getting interested in the last, since 1998 to 2000, in climate change. And Berkeley Lab was a fantastic place, and Berkeley was a fantastic place. A lot of Nobel laureates worked at Berkeley Lab. I think 15. But what people don't know, over 30 young scientists, graduate students, postdocs, or first job, career Nobel laureates were trained at Berkeley Lab. 30, over 30. So I said, if I can go there and convince more scientists to do something about energy and climate change, it would be worth it. So I said, okay. So I left in Stanford. Well, I didn't leave. They kept me on the faculty during the whole time as an active member. I had atomic physics still at Berkeley. Holger Miller was the senior person at postdoc at the time, and so, but the biology moved to Berkeley. And then I was thinking, okay, after 5 years I was going to step down. The people in the Department of Energy, not the Secretary of Energy, I got to know very well, and we became friends. But I was getting tired of it, and I really wanted to go back to lab, so I was going to stay at Berkeley, and I had some labs in the new Stanley building. And so in November, late November of 2008, I get this phone call and said, well, the president-elect would like you to fly to Chicago and talk about a very important job. And so I said, well, I'm not sure I really want to do this. I was going back to the lab. But how important is it? Secretary of Energy? Okay, maybe I'll go. The previous administration, they wanted me to throw my hand in as science advisor, and I said no, for a lot of reasons. But you never ever want to go as an advisor. There's a huge difference. If you go with budget authority, there's a huge difference. So I went to Chicago, and there's a rented floor space, and I go into this very warm room. I had a blazer on. I don't think I had a tie, but at least I had a blazer. But I had to take it off because it was really warm. And then 2 or 3 minutes later, the president-elect walks in, he goes up to me, and he's also, but he's from Hawaii, so that's why I think the room was warm. And so he says, a lot of people are telling me you should be the next Secretary of Energy. And so I stood up and shook his hand and said, who are these future former friends of mine? He ignored it. And so for the next hour we talked about it, and then I came back and I was very impressed. I went back and told my wife, if he asked me, I will say yes. And so he asked me, and I said yes. So there I go to Department of Energy, again, because I wanted to do something about climate change. In research in many things, but here's what was happening in the landscape. This is a graph of the cost of wind energy as a function of time from 1980 to 2003 or 4, 2012, sorry. And the cost, the green cost is going down. There was a little blip of supply chain stuff, but it's going to go down. And the amazing thing about wind energy today is in the Midwest, where you have the best wind. The cost of wind energy is actually comparable, if you take out the subsidy, it's comparable to a new natural gas plant, new, if you assume natural gas is $4 a million BTU, which is, it's $3 now, but historically it's been up and down and up to $12. So that was great. Solar, we have exquisite solar all the way, everywhere in the United States except two places, Seattle area and Alaska. And you know, and that blue color means there's not much sun. It's as bad as Germany, which has the highest amount of solar installed in the world. Okay. But the amazing thing is that very recently, the price of solar has come down. So this is the price of a contract. When you're a developer and you put in a big solar farm, and you go and borrow money and you build this thing, you won't get any money to borrow, or you wouldn't have anything to do unless you had a utility or a set of utility companies that says, we'll buy at a certain price for the next 20, 25 years. And in July of 2008, it was going for about 18 cents a kilowatt hour, above wholesale costs by a lot. And by 2014, it was going, these contracts are being sold now for a whole bunch of contracts for 5 and 4.5 cents a kilowatt hour, comparable to new natural gas. Okay? Now, what about deployment of both solar and wind? So here we have not much happened until 1990, and just putter along, nothing happened. This is installed capacity until about 2009. So then what happened? Well, I became Secretary of Energy. Now, you might say, you might say that correlation does not mean causation. But in this case, that's not true, because I was in charge of a loan program and was steward for the first loan we gave out, which was picked by career people, Cylindrum, and we lost a lot of money, 430 million. That's what happens when you spend too much time in DC. Millions become billions, anyway. But by 2013, 12 and 13, including all the losses for things like Cylindrum, net, the loan program felt that it's going to make the U.S. about $5 billion, including all the losses. Now, I was being steward for this. I had to personally approve these loans. Most of the loans we gave were to large solar farms and wind farms that the developers could not get Wall Street to loan anything at any interest rate. And so during that time, if you're installing something that's reasonably known technology and you had a power purchase agreement, the only risk is that you would be delayed in the construction deployment. But once you turn the switch on, you're going to be okay. So all the switches got turned on, and so we also loaned to Ford Motor Company. They were so deeply in trouble. GM and Chrysler already gone bankrupt and were owned by the government, but Ford was still a viable company. But they were in pretty big trouble. We loaned them $6 billion. We had to set aside $3 billion to Treasury as the loan insurance. So that means $3 billion for that loan meant it couldn't be used in roads or bridges or defense or education. Okay, it was a protection, mortgage insurance, if you will. So we set aside $10 billion. We'll probably lose $1.5 billion, but net, we're going to gain $5 billion. And the loans were being made at 1.5% to 2% interest from 2009 to 2013. Okay, so we weren't doing better at venture capitalists, we were doing better at Wall Street. And at that ridiculous interest rate, because we could have charged 5 and 6, because banks weren't going to loan for anything. The great news about this is that after that period of time, it's now bankable. You can go out and get loans from Wall Street. In fact, it's turning around that you can maybe get a lower interest loan to build a solar or wind farm than you can to build an offshore oil platform. okay? And the cost of renewables is the cost of money in large part, okay? So that was good. Some other things, I've started a few things. There's a thing called RPE, Advanced Research Projects Agency for Energy. It was modeled after DARPA. It came out of a report that came out, I think, in 2005 or 2000, something like that, called Rising Above the Gathering Storm. Norm Augustine was the chair of the committee. There were 20 people on the committee. I was one of them. And ironically, I was sent by the committee to go to Congress to plead for RPE in congressional hearings. I was sent to the Department of Energy to plead for their support of RPE. Congress gave me support, but the Department of Energy, even though Sam Bodman was a terrific person, the career people didn't want it. So I said, I'm sorry, they didn't want it. But he was concerned about climate. He steps down. 2009, the new administration, Obama comes into office, and the new Secretary of Energy was much more enthusiastic about RPE. And so we started it on Recovery Act funds. And after 2 years, it had enough support that it got base level funding, and actually a lot of Republicans, believe it or not, really liked it. There were other things I did, Energy Innovation Hub, Sunshot. I'm not going to go into this. There were a few things I had to deal with that were unexpected. I didn't really have to deal with this one, but I did. This is the Deepwater Horizon disaster where in the Gulf of Mexico in the spring of 2010, this is a BP, a number of others, and this thing catches fire, explodes. And Department of Energy has no jurisdiction at this at all. It's interior, it's Coast Guard, it's a lot of other things. But I made a suggestion to some BP engineers that turned out to be something interesting that I don't know how the president heard about it, but he heard about it, and after the end of a cabinet meeting, he comes up to me and says, "Shoot, go down there and help him stop that leak." Okay. So I assembled a team of half dozen other people. I thought of who I was going to consult a few others. Called one of them, said yes, and said, "Oh, by the way, that's great." Someone said I have to check my wife, I have to check the chair of the department, a few other things. They called me back that same day and said yes. It's great. Okay, we have to meet at 8 a.m. the next day in Houston, and every one of them came. And for the next 3 or 4 months, if they weren't there bodily, there were 2 or 3 emails a day, and it was amazing. The cabinet members looked at me and said, "Steve, you look really happy." And I said, "Yeah, I'm solving a technical problem." It was fun, in a macabre sort of way. Lots of pressure. Actually, the new CEO of BP, I kind of bonded because of stressful situations. You can bond, not trying it with the new guy. But this is what it looked like. And the CNN had this thing leaking every day. They had television every day, so there's a lot of pressure. I'm not going to go into this, but I just want to mention one thing. That summer, the surface of the Gulf of Mexico was 86 degrees Fahrenheit. Where the oil was leaking out 1 mile deep, it was 2 degrees above freezing. It remains that way all year round. This has to do with climate change because it takes a long time for the oceans to warm up. We don't know how long, perhaps a century, perhaps a century and a half. The damage we've already done, we don't know because we don't know what the new limitation is because the ocean is a cold sink. And only this year, they found out this plateau in the temperature, keyed in, but saying, what's going on, it defied computer predictions. They weren't, and we have these buoys that go up and down from the surface of the ocean down 2 kilometers to come back up. They telemetry, their temperature and salinity measurements. There are 4,000 of these, and in 2015, they said the surface temperature was plateaued, just like we knew. But if you average 0 to 2 kilometers deep, it accounts for all the heat. Okay? The ocean mixing increased a little bit. And so the excess heat was going there. Anyway, okay, I learned a few things in government. The first cabinet meeting, I told the president, I learned a law of motion, that something in motion in a big bureaucracy will come to a screeching halt unless continually pushed. Newton was wrong, Archimedes was right. You know, there was so much friction. If you didn't want something to happen, you just, unless your boss pushed it, you can kill it by just not doing it much. It just stops. But I also learned that how to make decisions, and there are a lot of things I didn't know about, but you've got to make decisions on expert knowledge and knowing what questions to ask. And the other thing I learned after year 1/2 is that you don't be concerned about, quote, tactics. You can be concerned a little bit about tactics, but if you think too hard, it's not going to be good, and so you actually have to make decisions based on some core values. And that helps a lot. Lesson number 2. This is I knew beforehand, but you know, very good people, great people hire people better than they are, and they don't hire assistants, they hire proteges. So in short, A's hire A's and B's hire C's. Because if you're an A, you're not going to be insecure, and you want people around you that are as smart, even smarter than you, and if otherwise, you don't want those types. And what I saw was that you can spot a mediocre manager. They want to brief you, they don't want people below you briefing you. In fact, they don't want the people below them briefing anyone except them. Rather than, you know, they're your proteges, which means you've got to push them out there and talk to everybody. And so a sure sign of mediocrity. For lesson 3, you have to attract and retain the best people. My pitch, I called up a lot of people, friends I knew, got a lot of them to come, and it said, well, look, you know, I know you're going to give up a lot. I give a lot, but come join me, even if it's 2 years, 4 years, I don't care. But just come join me, maybe 8 years, because we're trying to save the world. And then, and a lot of people did have a lot of personal sacrifice. Arun Majumdar, Rajiv from here from Berkeley, Rajiv from MIT, lots of people came. I didn't get everybody, but I got a fair number. And you should let your proteges spread their wings. So if I look back in the Department of Energy, it wasn't really the programs I started. You know, you can start a program, but then you hire someone terrific like Arun Majumdar and Dave Davidson and others, and you let them run with it. And mostly you protect them from the rest of the bureaucracy. You own it, I'll protect you. And it was called blocking and tackling. And that's something so that the bureaucracy doesn't drag them down. What I didn't like was dealing with the press. They play gotcha, they're vicious, they're venal. And so when it was decided I was going to step down by my wife, she denies this, but she was great. She came and when we took the job, I had to resign from Berkeley. So it means I couldn't have a factory mortgage, which means we couldn't maintain the house and have an apartment, so we had to sell the house because no more factory mortgage. So she decided she was going to come with me. That's great, hygiene. But after 4 years, which every month she'd go back and visit the grandchildren, she said, well, you know, she looked at me and said, no one's irreplaceable, not even you. And so it's time to go back home. And I'm going, so I decided to follow. Now, where was I going to go? Well, I didn't want to be a president of the university. I didn't want to be head of an institute. So I wanted to be a faculty member. So the natural choices were Berkeley and Stanford. But again, because of 4 grandchildren, son and daughter-in-law who were at Stanford, the daughter-in-law is on the faculty in medical school. we went to Stanford, so there was no choice. So I told Stanford that there will be no counteroffer. I'm not going to ask anyone else for a job, and all I want to be is a faculty member. All right, so that was in play at the end of 2008, in November, late November 2008. I told the president, I'd love working for you. I'd love to stay another couple of years, but this is the way it is. I understand. So we talked another half hour about what, I would recommend. So I was allowed to make an announcement on February 1. It was announced that I wrote a letter, an open letter, to the employees that I was stepping down. On February 7th, 6 days later, The Onion runs this story. Hungover energy secretary wakes up next to solar panel. And I'll just read you this excerpt. Sources have reported that following a long night of carousing and a series of DC watering holes, Energy Secretary Stephen Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, Chu's encounter with the crystalline silicon solar receptor was his most regatta dance since 2009, when the extended fling with a 90-foot wind turbine nearly ended his marriage. Now, so I walk in, on February 7th in the morning, I walk in, head of public affairs says, we don't normally answer scurrilous newspaper articles, but I think we should answer this one. And say, oh yes. So that noon, we issued the following statement. I just want everyone to know that my decision not to serve a second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar power is a growing source of U.S. jobs and is becoming more and more affordable, so it's no surprise that lots of Americans are falling in love with solar. Now, I have to say also that my wife stood by me on this. She looked at that picture and said, you don't have hair on your arms. Anyway, so then back to Stanford, and during the time I was Secretary of Energy, some spectacular things were happening, actually before that time. And the 2014 Nobel Prize in Chemistry was given to 3 physicists, as it should be, no. for their development of new methods to push the optical microscopy to new heights. And so, so this is W.E. Murray at Stanford, Eric Betzig at Genelia Farms, H.H. Mai, and Stefan Hell. Okay, so let me just show you what you would see in an ordinary microscope. This is the Eric Betzig article, 2006. That fuzzy thing on the left is a section of a cell. That's what you see in an ordinary optical microscope. The thing on the right is this so-called super resolution. And if you blow up that little section, you get something that looks like this. And you can actually locate the position of molecules with about 10 or 15 nanometer precision instead of 250. It's more than an order of magnitude, 25 times better. And when I was at Berkeley, and then I went to the Department of Energy, but I had some postdocs, we were working on this as well. Basil Burke published, and others published a paper in 2012 on this is a single cell, we call it a single cell, that's what you would see. But this is what you can see in the super resolution, and you blow up that, and you can see that. So the first thing was done on dead cells. This was actually done on live growing biofilms, but it was a rigid cellular matrix. So if you go and look, so then I'm leaving the Department of Energy, and there were a lot of experiments. We in the field of biology, biophysics, said there was a lot of things we want to do, but what were the limitations on these super resolution techniques? Well, it takes about a minute to form those spectacular images. It's getting a little bit better. The best images are dead stuff, and or in rigid cellular matrices, which was that other picture. If it's rigid, it's not moving around due to Brownian motion. And so the Brownian motion would smear it, and you would get no better than optical resolution. So if you can develop nanoprobes that could allow this spatial resolution, not on just 1 or 2 proteins, but in half a dozen, and you can get them bright enough, and other wish lists, maybe that would be cool. So when I got back to Stanford, I started thinking about that. It's liberating. By that time, my group was 0. I let my postdocs take the apparatus with them, so my equipment was 0 minus epsilon. My lab space was gone, my home was gone, everything was gone. My wife was with me, it's good. So whether it was a 10-year sabbatical or a 4 and 30-year sabbatical, it actually says you can step back and start something new. So one of the things is, could you put rare earth elements in nanocrystals? And so we started doing this in collaboration with Paul Alvasados, a graduate student of his, Alexander Cordius, and one of my postdocs. And the idea is, this is neodymium. This is a rare earth that is one of the workhorse lasers. You can excite it a certain wavelength, and it gives very narrow emissions. And so we started fooling around with this. I'm not going to go into technical details, but you can put different rare earth elements in these nanocrystals. You can make them 5 nanometers, 10 nanometers, 20 nanometers. You can put neodymium and you see light at that green wave, that green curve at 875 nanometers. Ytterbium, redder, thulium, bluer. So let me just point out a few things you can do with this. You have one class of crystals, you put a rare earth in it that you want to label a particular cell or a particular protein. You put, in another class of crystals, you put 2 rare earths in it. Thousands of impurities per 20 nanometer or 10 nanometer particle. So it gives out 2 colors. Or you can put another one that only has 1 color, or you can put in another one that has high in one, medium in another, none in a third. And so you get the idea. Each crystal, you can add combinatorial shades of colors, because it's not a single emitter, it's thousands of emitters. Okay? So you can make a spectral fingerprint for each class of crystals. You try to label a particular protein or a particular cell. And so you can easily work out that there's, dozens, 3 dozen proteins. Okay, if you were labeling cells, individual cells, you can take this image, a microscope objective, where's my thing, and you can project half of it onto where you can center the cells, that's the lower array, and the other side you can put a prism and you can display the prism. So if they're well separated, you can do this. But the real cool thing is, if you're looking for a cluster of proteins within a very small area, like 10 or 20 or 30 nanometers, so within that, what can you do? So let's consider this one cell with this one protein, a set of proteins within a cell. You want to see them if they're interacting. Because the rare earths have a narrow band of excitation, you can use one laser to excite certain colors, and you can image that. You read it out on the camera. You use another laser to excite another rare earth that could be in very close proximity within an optical wavelength, and you read that out, and then you read it out. And so you can start to read out a half a dozen to a dozen different proteins, all within 10 or 20 nanometers. So that's another advantage. A couple of us got excited about this prospect, and so we submitted. So the Moore Foundation gave me a lot of money, or not so much money, but enough at the beginning. And then Tom Sudoff, me and Lu Chen Lo said we can do a lot of neurobiology with it. And so we put in an internal proposal to Stanford, so we got some seed money. And so I can't go into those things. But there's other particles, fluorescent nanodiamonds. This is in collaboration with Nick Balash and ZX Shen at Stanford and Lena Vukovic on the quantum stuff, but it's mostly about growing very small particles of diamond. On the left-hand side, you see these small diamonds. They're a micron in diameter, but they're nearly perfect diamonds. So it's something you can be proud to propose to someone with, because they're really very perfect. We can make them even smaller, and the image on the right is a diamond based on a lot of things, but it's now less than 10 nanometers. So we're making stuff like this. There's some good stuff, there's some bad stuff, but things are happening. Another thing about the rare earths, not the nanodiamonds, the rare earths, they give out the light hundreds of microseconds instead of in a nanosecond. And you remember, you're compensating by putting in thousands and thousands of emitters to make them bright. But so usually you take a microscope objective and you put it on an array camera. But something good is happening. The lifetime is so long you can put a mechanical chopper in here and spin a wheel. And when you're exciting the probes, the camera is blocked. And then it spins and it lets light through and you expose it and then it closes. But if you work out how good a focus you need, it turns out that you need a pretty hard focus in that center spot, which you can do. But instead of using a metal wheel, you make a glass wheel and you chrome it. And so that is happening. And so my former technician at Bell Labs was the founder and sole owner of Thor Labs. And so he's making this wheel. He's a great, Alex Cable is a great guy. He was so thrilled I was going back to research. I didn't ask him, but he gave $100,000 in my discretionary fund research the first year, and then next year he gave another $100,000. So I'm hoping this is a good trend. We're working on a few other things with him and others. There's another application. You can take an electron microscope, and electron microscopes give beautiful images, black and white images, but you can't identify specific proteins. Okay, so if you have these probes, these rare probes, and collected the light, so normal electron microscope is scanning around, when the spot is at a particular point, you also collect photons. And so these are some samples that Nian Liu made, a postdoc in my lab, and then Peter Mara and Max Krieger and two other postdocs had this bright idea that you can collect different color light, therefore you can identify different proteins, but with the same electron microscope. So again, very preliminary data. The left-hand side is the scanning electron microscope picture of nanoparticles. On the right, this is the color. So it's only fluorescence on the right. Let me remind you, this is a cell. It's a cancer cell called a HeLa cell, and the scale bar is in the lower left, just 1 micron. So this is a cancer cell, but we're going to blow up that little white thing on the bottom. And so when you blow up that little white thing on the bottom, you see the electron microscope image on the left, and that's the electron microscope image, but the thing on the right is the luminescence. But because you can block during the excitation, you actually, you can see the cell, but we've already demonstrated you don't have to see the cell in luminescence. You just see the particles. And so we're very excited that perhaps we can get 10 nanometer resolution simultaneous with the electron microscope, but now identifying half a dozen different proteins. So we're actually doing this work at Lawrence Berkeley lab in a home-built SEM and light collecting, because we don't have that at Stanford. So anyway, at the moment. I'm going to skip this, go a little bit to batteries. In 2008, the manufacturing cost of batteries was very high. It was $1,000 a kilowatt hour. And then in 2012, it was half the cost. In 2011, we got together in the Department of Energy and said, let's set a goal and a roadmap and see how good batteries can be. And we thought by 2022, if you can get automobile batteries at $160, $150 a kilowatt hour from 1,000, or utility scale storage at less than $100 a kilowatt hour, you would have $100 billion a year market per year. Okay. In fact, the first time in the history of the Department of Energy, we said at what price point, how big the market would be, and we started to make decisions on the applied areas. So they thought we were smoking something. You know, it's from Berkeley. Anyway, they also thought the same thing for our solar program, which turned out to, we achieved the goals in the solar much earlier. Okay, in batteries, how are you doing? Well, this is, the blue curve was a projection from Bloomberg New Energy Finance, and the red X's were the manufacturing costs ahead of schedule. If the gigafactory, when the gigafactory gets built, it will, by sheer manufacturing volume, mass production, drop the cost to the goal we thought would happen in 2022. Now, I put the date as when they're going to do this in 2018. The original from Tesla was 2016, but you raised the initial price from what was projected and slided time back, so-called Elon Musk factor, and it was still going to be way ahead of anything. It was great. Okay, so energy density was, in per unit volume, was making, you may not believe this, but the battery in your cell phone has 3 or 4 times the energy density of the first lithium-ion batteries that Sony introduced. It's just that display uses a lot of electricity. Okay? And so, but the energy per unit weight has only gotten better by 20 or 30%. And so I started working with a professor in material science, Eastway, and the best that you can do was the carbon nanos, which are today's lithium-ion. They're somewhere around this energy density. There are a number of battery companies trying to make silicon with that energy density. And for the last year or 2 years, we've been trying to figure out if we can make a lithium metal with a sulfur in a 3-dimensional geometry. To use nanotechnology, my motto and what I was pushing was the battery has to last longer than the human bladder. What do I mean by that? It's rare that you would drive more than 200 miles without a pit stop. During the time you're having this pit stop, can you recharge the car? You know, charge, discharge. If you have equal time, it's okay. And if you can make it really cheap. Now the costs are going to plummet, but if you can get this higher energy density, the Tesla battery, well, this is, oh, I didn't correct the numbers. The full weight is about 12, battery pack and everything is about 1,500 pounds. Cost maybe $30,000 to make the long-range Tesla. They're not telling me exactly how much it costs as proprietary information, even though I loaned them $460 million, which they paid back early. They paid back in full. So, in any case, we don't know whether we're going to be able to do this, but I know of other smarter people, but there's a whole bunch of people who see this as something that could change the world. Because if you can get a 300-pound battery that allows you to go 300 miles or 250, 300 miles, and the cost is $160, then a $25,000 car becomes, without subsidy, becomes a reality. And the amazing thing about an electric vehicle is you can have your smartphone and you push the button app and you say, it's get the car ready. If it's cold in winter or it's hot in the summer, cool it down, warm it up. It calls you back and says, car's ready, we're ready and waiting to go, where are you? In a gentle way. Can't do that with an internal combustion engine vehicle. Okay? So once you have that capability, and you know, you can do this. Yi and I are working on air filters. It turns out that small particulate matter is maybe far more dangerous than we had imagined. And there's papers in 2013, a large meta-study, that said if you have every 10 micrograms per cubic meter of PM 2.5, you have a 1.4 increased chance of getting lung cancer. Okay, and okay, so that's a little scary. If anyone has been to Delhi or Beijing or Shanghai on bad air days, you immediately have respiratory ills of some kind. So where's the number? 10 micrograms per cubic meter, 1.4 higher chance of getting lung cancer. So wherever you see red is higher than 100 micrograms per cubic meter, 10 times more. So the math is you multiply 1.4 10 times. If this turns out to be correct, we will know in a while. How long will it take? About 30 years, 20 years. Because it's only been really 10 years since it's really bad. Let me remind you how long it took to do cigarette smoking. This is cigarette smoking, 1900. This is the number of males who smoked cigarettes by the middle 1960s. The average per capita consumption of cigarettes was 220 packs a year, including the non-smokers. Take the whole male population, adult male population, and divide by the consumption of cigarettes, and that's what you get. In the mid-50s, lung disease was a very rare cancer, and it started to grow. And so in the 50s and 60s, the medical community said, what the hell's going on? You know, there may be a correlation or causative effect between smoking and lung cancer. The tobacco company said, no, correlation does not mean causation. You can't predict who's going to get lung cancer, who's not. I've got a grandmother who's been smoking all her life. She's very healthy. She's wrinkly, but she's healthy. And you didn't understand, and science can't predict who's going to get it and who's not, so this all could be just a chance correlation. Massive education campaign to keep kids from smoking. Smoking goes down. Lung cancers follow, but there's a 25-year lag. It's the same with climate change. The same people have been hired for the fossil companies to say that correlation, causation, you know, the climate may be changing, but it may not be caused by humans, and, you know, what's the problem? And the problem is it's not a 25-year lag, it may be a 100-year lag. And so that is a problem. Now, when you're smoking, the risk is mostly on you. There is some secondary smoke, but it's mostly on the smoker. But the whole world is smoking and fossil fuel, so to speak, and so it remains in the atmosphere. By the way, the women cancer deaths lagged because women didn't smoke as much, but they were catching up. So this is another issue, both in smoking, but now PM 2.5, as well as climate change. So I'm going to end this by this image. It's the first mission to orbit the moon in preparation for Apollo 11 landing. And in the last orbit around the moon, the astronauts turned the capsule earthward, and one of the astronauts took this picture. And he said, we came all this way to explore the moon. The most important thing is we've discovered the Earth. So if you look at that picture, the moon is not a friendly place to live, right? And the Earth from that vantage point looks pretty good, right? And there's nowhere else to go. Now this was taken in Christmas Eve 1968, but since that time we're becoming more certain the climate's changing. There's very compelling evidence that it is mostly caused by humans. Very compelling isotopic evidence that this is not a natural cycle. This is fossil fuel carbon being liberated. And so this is the issue. This is why I took this 10-year sabbatical. and again, a very strange random walk. I'm still trying to work on it. And I think we really have a moral responsibility, because the most innocent victims will be the poorest citizens who don't have the means to adapt, and people yet to be born. But here's the problem I find. If you're smoking, okay, you bear the risk. So we as a society, if we're not willing to spend half of 1% of the GDP and say, well, we're not really sure. We're not sure what's going to happen. So until we're sure, why should I change my lifestyle? You know, that's not my problem. And it's not, you know, it's not going to be the problem of my children mostly. It'll be the grandchildren and great-grandchildren and people halfway around the world that I'll never meet. So it's not a problem. And so this is bad news. So I would remind you there's an ancient Native American saying, we do not inherit the land from our ancestors, we borrow from our children. One slide closing picture, so in this really strange random walk, going away from fundamental science, poking my nose in things and not knowing anything about anything, and just hoping it's neat and cool. And, you know, so I always look to Gene for approval. He wasn't so sure about laser cooling trapping for the first couple of years, but I think he came around. And so, anyway, I'm hoping he was thinking. Thank you.